Here, let's try an example which demonstrates the relationship between a function and its inverse function graphically. In this case, we want to sketch the graph of the function f of x equals the square root of -1 minus x, and its inverse function on the same coordinate axes. So let's just kind of remind ourselves for a moment what this function might look like. So in this case, it looks like a square root function that has been shifted and reflected, because here we have a minus in front of the x, and then shifted 1 unit to the left. So it's being reflected in the x-axis. It's being reflected in the y-axis and then shifted to the left 1 unit. So we can imagine here that graph might look something like this. Okay, so that would be our original f. What would the graph of f inverse look like? Well, let's see, if we were to reflect it in the line, or consider the symmetry with the line y equals x, the graph of f inverse would look like a downward parabola there. In this case, it's half of a parabola. We notice that exhibits the symmetry that we know. And we can kind of also think about what graph here we're actually drawing with f inverse. So let's just quickly solve for f inverse. We know here that if I write y equals the square root of -1 minus x, I can square both sides to get rid of the square root, and then isolate the x. And there we have x equals -y squared minus 1. So our inverse function there is -x squared minus 1, and we see that in the graph here that's exactly what we see, but notice that it's only half of the parabola. So here we're looking at the restriction where x is positive. And why do we have that restriction? Well, if we look at the square root here, we have to assume that y is positive, because square roots, remember, only output positive values, or non-negative values. And so the same should hold here when I interchange x and y to get f inverse of x. The same should hold true for x, that x has to be non-negative. And that's exactly what we see in the graph of f inverse here. This is downward opening parabola with shift downward one unit. So with this in mind, we can start to think about performing calculus with inverse functions. And one important idea is that if a function is continuous, then its inverse function is also continuous. So this is pretty easy to visualize graphically. If I have a continuous function, we know its graph would be a continuous graph, and so its inverse function certainly should also be a continuous graph. So it makes intuitive sense why this theorem would be. And once we've thought about continuity, we can also think about differentiability as well. And if a function is one-to-one and differentiable with some inverse function f inverse, then the derivative of our inverse function can be found using this formula here. But here, before we prove this, let's think about it graphically. So if I'm looking at the point AB here on my inverse function, and I'm looking to find the slope of a tangent line at that point, well, we can imagine the slope there has some rise over 1 run delta y over delta x. And how would that relate to the slope of our original functions? And what I notice here is the original f, right, has the point b comma a. And so AB here corresponds with the point where x equals to b on the original function. And there the slope is going to be delta x over delta y. So it's like the rise over run switches on the original function there. And really this then could be written in terms of that slope there, delta x over delta y, just by flipping this over. And so there we have 1 over the derivative of the original function f, in this case at b. So it's 1 over f prime of b. Oh, and actually here I meant to say this is the derivative this was meant to be the derivative of the inverse function here. Sorry, so here we were looking at the point a, b on the on the inverse function, and the derivative at a, right, was the slope delta y over delta x. And then here I wrote it in terms of the derivative at b on the original f. So that's one way to kind of think about this relationship graphically. But here I'm going to maybe prove it using a rule that we've already established. Okay. So in particular, we know that if I do the composition f composed with f inverse of x, this should equal to x. And therefore, if I apply the derivative to both sides of this equation, on the left-hand side, we're going to apply the chain rule. So I would have f prime of f inverse of x times the derivative of f inverse of x, which I'll just write f inverse prime of x. And then on the right-hand side, just equals to 1. And there, if I isolate f inverse prime of x, I get the formula that we have above. So in other words, 1 over f prime of f inverse of x. And this will be valid as long as this denominator is not equal to 0. So that's part of the assumption here that we're making as well. So let's try an example where here we're considering the function y equals x squared restricted to the domain x greater than or equal to 0. Now, of course, we know that y equals x squared, the whole graph, I'm picturing the whole graph, not on its restricted domain, but the entire domain, certainly is not one-to-one. On this case, though, we're restricting the graph from 0 to infinity. So if we're restricting it, so it is one-to-one, since we're restricting it to the domain from 0 to infinity. So what would f inverse prime of 1 equal to here? So notice here I'm not going to bother finding the inverse function because our formula here only depends on f prime of the original function. Okay? And in fact here we know that because here on the graph of f it contains the point 1, 1, So we know that f of 1 equals 1, so therefore f inverse of 1 also equals 1. So this will equal to 1 over f prime of 1. So really, we just have to find the derivative of our original function, x squared, which of course is just 2x. So this will be 1 over 2 times 1. Notice here, I didn't have to find the inverse function. Of course, that would be an alternate way to do it. In this case, finding the inverse of x squared is pretty simple because you can just take the square root. In other cases, though, it might not be so simple. And so actually going through and constructing the inverse function may not be necessary, and it may be more work than it's worth. Here, let's try an example with the function f of x equals 2x plus cosine x. Here again, we want to find f inverse prime of 1. So f inverse prime of 1, according to our formula, would be 1 over f prime of f inverse of 1. So let's take a second here to try and figure out what is f inverse of 1. So we want to think what input value here will give us 1. Because if we can solve that, then we know what f inverse of 1 is. So let's try and solve this out. Let's take 2x plus cosine x, equal that to 1. So what would be a solution here to this equation? And in this case, maybe I can just do this one mentally, because I know, for instance, that cosine of 0 is going to equal to 1. Right? So therefore here f of 0 equals 1, which means that f of 1, or sorry, f inverse of 1 equals 0. Now there's another question, which is this the only answer? Is this the only value of x that'll equal to 1? So in other words, is this function 1 to 1? So one way you could verify that this is in fact 1 to 1 is to show that it's always increasing. Let's just quickly verify that. Notice that f prime of x here is equal to 2 plus negative sine x, or here I'll just write minus sine x. And then sine x, we know, ranges from negative 1 to 1. And so this is always going to be greater than 0 for any value of x, which means that f is always increasing. And if it's always increasing, then we know it's 1 to 1. So now we've kind of established how we're going to solve this. We found f inverse of 1, which is 0. So we're going to do 1 over f prime of 0. And in fact, here we found f of 0. I'm sorry, we found f prime. So now we'll just evaluate that at 0. Which leaves me with 1 over 2 minus sine of 0, which is 1 over 2.